In a previous video, I used 2014 SAT and teacher salary data from each of the states to illustrate how to analyze the relationship of a categorical and quantitative variable. I'm going to use these data again, but this time to illustrate how to analyze the relationship among two quantitative variables. I'm going to select the variables starting salary and average salary for this analysis. Why might such an analysis hold any interest? The analysis should tell us something about similarities and differences across the states regarding pay raise policies. We will talk about this as we proceed. I suspect that understanding something about how a state handles pay raises could be of interest, especially for teachers. Here's the codebook for our data. We are going to focus on the last two variables listed here. The unit of measurement for both variables is dollars. I will begin by loading the data. Next, I'm going to use a trick that I discussed in an earlier video that should make it easier to understand our analysis. Rather than having numbers that are in thousands on my two axes, I'm going to convert the unit of measurement to thousands of dollars so that I will be dealing with only two-digit numbers on each axis. I divide the starting and average salary by 1,000 and store these in new variables. These new variables now have a unit of measurement of $1,000. Let's plot the relationship of starting and average teacher salary. It should not come as a surprise that what we see looks like a strong positive relationship. That is, states that pay a higher starting salary are also more likely to pay a higher average salary than those states who pay lower starting salaries. This doesn't necessarily reflect the policy and priorities given to education. It may, but it may also reflect different cost of living in different states. Let's do a simple linear regression analysis, regressing average salary on starting salary. Now let's use the results of this analysis to place a regression line on our plot. What really interests me is the effect size measure, that is, the slope coefficient. So I'm going to use the coefficient function to obtain the two coefficients for my regression equation. The slope is about 1.4. That's interesting. This tells me that, on average, if we look at two states with starting salaries that are $1,000 apart, the average teacher salaries for these two states will be about $1,400 apart. Why isn't it still $1,000 apart? That's what we would expect if, in every state, the annual increase for teachers was approximately the same for all teachers, regardless of other factors such as years of experience. By the way, that would result in a slope for our regression line of 1. On the other hand, if states were to provide a percentage increase whenever they give teachers a raise, those teachers who have been in the system longer and are already making more would receive a higher increase. Further, if the state starts the teacher at a higher salary and then states provide similar percentage increases rather than fixed amounts, the average teacher salary would increase more than in states that have a lower starting salary. In short, there are a variety of possible explanations. All we know for sure is that differences in starting salary are associated with even higher differences in average teacher salary. How good is the model? Let's get the correlation coefficient. That's about 0.81, so this is a strong model. Residuals about the regression line are relatively small. Let's calculate the coefficient of determination. That's 0.65. Thus, we can say that the starting salary of teachers in the states explains about 65% of the variation in average teacher salaries for the states. Now let's learn something about the individual states. I'm going to create nice, understandable variable names for each of the variables that I'm interested in, and then put these together in a new data set. I'm going to create a variable with the state name, one with the starting salary, one with the average salary, one with the predicted salary, and one with the residual. I am going to use a function called data.frame. This creates a new data set with the variables that you provided as function parameters. I'm going to create a new data set that I'm going to call state.data. I will use the data frame function with each of my new variable names to populate this new data set. Now let's view the data. Let's scan the residuals. Most of these are quite small, as we expected given the strength of the model. Here's one that's double-digit. This is for Massachusetts. It's a positive residual, which means that Massachusetts is paying an average teacher salary that's even greater than we would have predicted based upon their starting salary. Perhaps Massachusetts has decided to reward experience. We would have to investigate further to see the reason for this residual. One of the primary purposes of residual analysis is that it helps us identify cases that we might want to investigate. Whatever the reason, the model predicted that the average teacher salary based on starting salary would be about $60,800 per year, but instead, the average teacher salary in Massachusetts is $72,300, or at least it was in 2014. Here's a state with a relatively large residual in the negative direction. That state is Texas. At the time these data were collected, Texas was not increasing teacher salaries at a rate that is consistent with the other states. Again, the residual analysis can lead us to investigate further. But we don't have enough data to make judgment calls. Perhaps Texas offers other benefits besides pay that are not reflected in the salary data. Then again, maybe Texas did not decide to put a priority on education and teacher pay. We don't know. Let's look at South Carolina. In 2014, the starting pay was $32,300 and the average pay was $48,400. To be consistent with average relative pay increases across all states, South Carolina would have an average teacher pay of $48,800. So it is about $400 per year below that, as reflected in the residual of 0.4. Remember that the unit of measurement is now in thousands of dollars, so 0.4 means $400. We analyzed the relationships of these two quantitative variables graphically with a scatter plot and a regression line, and descriptively by looking at effect size, the slope of the regression line, and measures of association, the correlation, and the coefficient of determination. We also studied residuals to help us select interesting cases that we might want to investigate further. We saw how we can focus on a single state of interest and look at predicted values and the residual to better understand that state. With this example, we wrap up, at least for now, our study of how to analyze a bivariate quantitative relationship. we have one more two-variable relationship to look at: the association among two categorical variables. I'll begin that in the next video.